Hello and welcome. In today's video, I want to have a chat about what I personally find fascinating in deep learning and what I'm currently writing my master thesis on. Deep learning and neural networks can do so many amazing things nowadays. We're getting closer to self-driving cars that are totally autonomous. There are now robots that jump over obstacles and who might soon work in our homes or in public spaces where we might interact with them. There are digital assistants like Siri or Alexa in nearly every home now. They seemingly understand what we say to them. But I'm not really one that's interested in the newest transformer or whatever neural network model is making all of these things possible. I care more about the basics, like the core of every deep learning problem. Because what was fascinating to me when I started looking into deep learning because of a seminar I did in university last year was that no one seemed to actually understand how it works. Because everything I had been learning up until then in mathematics or computer science, it was maybe complicated, but if you spent enough time to learn it, then you would understand it. Like, there was no mystery to it. You had to work hard to understand it, but it was all explainable. But then I looked at deep learning, and it is a super powerful thing that everyone around me was either already using or wanted to use. It's this huge hype. And I read a few chapters about it, and I remember stumbling upon the word generalization. And I didn't really know what it meant in the context. And so I looked it up, like you do. There are, of course, definitions for it that explain it, like generalization error is the difference between the test error and the training error. Or for image classification, generalization refers to the ability to classify previously unseen examples correctly. You could say generalization is the ultimate goal of training neural networks. We don't want the networks to be just good on the training dataset. We wanted to solve a problem in general, which is sort of where the word generalization comes in, I guess. The goal is to find what all of these examples have in common and to understand it in such a way that you're the network here, can apply it to all other general examples. So I found all of these descriptions of generalization, but I kept trying to find the answer to, okay, but how does it work? How do those neural networks generalize? Because we never tell them that we want them to do this. We show them the same training examples over and over and over again, and we just hope that they find a common ground, maybe in between all of those data points, and that then is good enough to generalize to all other examples. But that's just what we want. We never explicitly tell the network that. But I didn't find any answer to that. It took me a few hours of confusion to finally find some recent research papers about the topic that clearly stated that while we have some rough ideas about how it might be working, we don't actually know. There is no mathematical proof, no definite answer as to why stochastic gradient descent and other optimization methods actually find a point in the parameter space with which the network can then classify other images correctly. Now, I know that many people don't care about why or how it works. After all, you could argue the only important thing is that it does work. And it does work really, really well. However, there are many important discussions going on about the fairness and the ethics of AI and deep learning in specific. Like, for example, should the government be allowed to deploy face recognition software in public spaces to fight violence and crime? Would that maybe affect specific minorities unfairly? And in general, how can we make sure that these amazing new technologies do not hurt anyone or treat them, like I said, unfairly? And I personally feel like we will not be able to answer many of these questions without understanding how and why the technology works at all. Now, a quick disclaimer. I don't claim to be an expert on the topic or to have read every single new research paper that has come out in recent months. I'm still myself a student and in the process of understanding how all of this works, so please don't quote me on this incoming ramble of why this particular topic piques my interest. My supervisors in university have, however, approved my research topic for my master thesis, which deals exactly with better understanding how stochastic gradient descent finds good minima and what they might look like, so I'm quite certain that this is indeed an open research question. Now let's talk a bit about what I call the illusion of gradient descent. We all probably know those images of gradient descent where we have a hill and there's a ball or a point on it and it's going down the hill towards a basin or a valley. And that is a really great visual example of what gradient descent in essence does. And it's good that we have this visual example because it allows us to understand it without having to look at the code or the formulas behind it. But we have to keep in mind that these images are extremely simplified. They don't show the drastic nonconvexity or over-parameterization of the problems at hand. Let's first talk about nonconvexity. In the classic gradient descent example, we might have a ball which is already on a slope and it then goes down to the minimum. But none of these visual examples take into account saddle points or the various ups and downs that a non-convex function has. There are many open questions in this. For example, why are we able to find a good minimum after we optimized our hyperparameters, of course, even though we start at a random initialization, so we start at a random point? Why do we still mostly get to a good minimum? And what do those good minima actually look like? Do bad and good minima actually look the same, but they are just at different heights in the loss landscape? I mean, to me that sounds entirely reasonable, but then how does stochastic gradient descent tell them apart? How does it know to go to the lower minimum of the two? If you're interested in this sort of discussion, you might read up on flat versus sharp minima, and I'll link some of the papers that I've read on the topic down below. The general first idea here is that flat minima are more desirable because they will generalize better, and that stochastic gradient descent will naturally go towards those instead of the sharp minima. What those images of gradient descent of a ball going down a slope also don't show is that we are in a parameter space of millions of dimensions, and we can only show 2 of those dimensions because we need the third dimension that we can draw for the loss value. But we are not just going left or right or up and down. We have millions of directions to choose from and somehow still end up in a good minimum if we use stochastic gradient descent. To me, that's just very hard to wrap my head around, that there are millions of directions. Like, I can't even consider what 5 directions or 5 dimensions might look like, but there are millions. And stochastic gradient descent somehow deals with that. But it's so hard to imagine what that might look like. Another thing that we should consider is that the networks are heavily over-parameterized. That was also something that wasn't completely clear to me when I started, because I was used for machine learning that we have less parameters than we have data points. For example, if we do linear regression, then we don't want the line to fit every data point because that would be overfitting. We want it to be somewhere in the middle, and to achieve that, we use less parameters so we can get a general idea of the problem. And because of that, there's also likely only one optimal solution. There's only one global minima where we can approximate all of the data points to a point that is just the best that we can do. There is one best that we can do solution, but not so in neural networks. In modern neural networks, we have over 100 million parameters in a model, and likely less than those in data point examples. That means there will likely be many different global minima that are all equally as good if we just look at their loss value. How do we, or rather stochastic gradient descent or other optimization methods, choose between all of these good minima that look equal at surface value? And how is it that SGD tends to find the minimas of those that will also generalize well to unseen images? And also here, if you want to know more about this topic, I suggest you search for research papers with the keywords implicit bias or regularization or implicit regularization, and I will also link a paper that I've read on the topic in the description box. So there's really no good conclusion to this video, but I hope that all of these questions and research directions that I talked about explain a bit why I personally find deep learning so fascinating. And I would love if you would share in the comments what you find interesting about deep learning, and if I maybe piqued your interest with all of these questions as well. Thank you so much for watching, and I'll see you in the next one. Bye!